So Raptor 3 is designed to require no base heat shield, saving a lot of mass on the bottom and actually improving reliability.
Here's a number that should make NASA sweat. A single one of the engines on its giant moon rocket costs more than an entire SpaceX Starship booster, packed with 33 engines, one engine versus 33. And on May 22, 2026, SpaceX flew the engine that made that gap official. That engine is the Raptor 3, and it just had its first real flight aboard Starship Flight 12. So today we're putting it head-to-head with the legend it's accused of making obsolete, NASA's RS-25, the engine that powered the space shuttle for 30 years and now flies on the Space Launch System. By the end of this, you'll understand exactly where that obsolete headline is dead right and where it's flat wrong. Let's start with raw power, because the Raptor 3 is a monster. At sea level, a single Raptor 3 pumps out 280 metric tons of thrust. That's about 2.74 meganewtons, or over 600,000 pounds of force. To picture that, imagine lifting a fully loaded Boeing 777 jetliner straight up into the sky using just one engine, and the super heavy booster fires 33 of them at once, unleashing nearly 19.5 million pounds of thrust. That's more than double NASA's SLS, which clears the pad at around 8.8 million pounds of thrust, itself more than 30 times the power of a Boeing 747. The Raptor array blows past that and easily eclipses the legendary Saturn V that took us to the moon. But the truly mind-bending number is the pressure inside. The Raptor 3 runs at 350 bar of chamber pressure. Here's what that means in the real world. That's the crushing pressure you'd feel about 2 miles deep in the ocean, roughly where the Titanic wreck sits. Or picture balancing the full weight of a Chevy Suburban on a single postage stamp. That's what's happening inside this engine, continuously, while it's firing. And to force fuel in at that pressure, the Raptor's turbo pumps generate something like 100,000 horsepower. For comparison, the RS-25's main fuel pump alone puts out more power than 2 Nimitz-class nuclear aircraft carriers running at full speed, with turbines spinning 73 times faster than an Indy 500 engine. These pumps are violent screaming machines. Now here's the kicker, and it's the Raptor's secret weapon. It weighs almost nothing for its power, just 1,525 kilograms, about 3,300 pounds. Compare that to the RS-25, which weighs over twice as much at 3,500 kilograms. When you divide thrust by weight, you get what engineers call the thrust-to-weight ratio, basically how much muscle you get per pound of engine. The Raptor 3 scores around 184. The RS-25, 73. The Raptor is more than twice as efficient structurally, which means Starship can devote far more of its mass to actual payload instead of dead engine weight. The Raptor can also throttle all the way down to 40%, deep enough to gently land itself on a pillar of fire, something the RS-25 was never built to do. So at this point, it sounds like a total knockout. But hold on, because the RS-25 is not some pushover. It's one of the greatest engines ever built, and it still wins in 2 huge categories. First, efficiency. The RS-25 burns liquid hydrogen and oxygen, and hydrogen is the lightest element in the universe. That gives it an incredible vacuum-specific impulse of about 452 seconds. Specific impulse is basically a rocket engine's gas mileage, how much push you get from each pound of fuel. The Raptor, burning methane, tops out around 380 in vacuum. So pound for pound of propellant, the RS-25 squeezes out more momentum than the Raptor ever physically could. That's just hydrogen chemistry, and it's why NASA loves it for efficiency. Second, pedigree. The RS-25 design goes back to the 1970s. It powered 135 space shuttle missions. It has racked up over 1 million seconds of hot fire and flight time. It is arguably the most thoroughly understood, most trusted, human-rated rocket engine in existence. When you're strapping astronauts on top, that track record is priceless. So if the RS-25 is so good, why does everyone say it's obsolete? One word: money. And this is where it gets brutal. The $100 million figure in the headline is actually generous. According to NASA's own independent auditors, the baseline cost to build one RS-25 is about $104 million. But once you account for all the money NASA spent restarting the production line and upgrading these engines, the fully loaded cost balloons to around $146 million per engine. And the SLS uses 4 of them on every single launch. Here's the part that physically hurts. The RS-25 was originally designed to be reusable. On the space shuttle, they'd recover it, inspect it, and fly it again. But on the SLS, after about 8 minutes of flight, all 4 of these hand-built $146 million masterpieces drop into the ocean and are gone forever. NASA is taking a reusable engine and throwing it away. every single time. And the program level numbers are staggering. NASA's auditors project the agency will spend over $13 billion on SLS engines and boosters through 2031, helping push the cost of a single Artemis launch to a jaw-dropping $4.2 billion. Now compare that to the Raptor. Elon Musk has said the cost is tracking well under $1 million per engine, with a long-term target of around $250,000. That's less than $1,000 per ton of thrust. And SpaceX isn't hand-building these over years. They're cranking out roughly one Raptor every single day. So let that sink in. A single RS-25 engine costs more to build than manufacturing an entire 33-engine Super Heavy booster. For the price of just one of the 4 engines NASA throws away, SpaceX could build a whole rocket's worth of engines. And because the Raptor flies again and again, you divide that cost across dozens of flights, driving the price to put a kilogram into orbit down to levels nobody thought possible. That is the definition of obsolete. Not in physics, but in economics. So how did SpaceX pull this off? 3 big engineering moves. First, the fuel. Instead of hydrogen, the Raptor burns methane. Methane is slightly less efficient, but it's about 6 times denser, so the fuel tanks are smaller and lighter. And here's the genius part. Methane can actually be manufactured on Mars, using the planet's atmosphere and underground ice. That's the entire point of Starship. Using a chemical process called the Sabatier reaction, future robotic factories could combine Martian water ice with carbon dioxide from the thin Martian air to brew fresh methane and oxygen right there on the surface. You literally make your return fuel on another planet. Hydrogen simply can't do that. Second, the engine cycle. The Raptor is the first full-flow staged combustion engine to ever fly. Without getting lost in the weeds, this design uses 2 separate turbopumps and burns all of its fuel and all of its oxygen, which lets it hit that insane chamber pressure while running cooler and safer. It also makes the engine safer, because the fuel and oxygen never mix until the main chamber, eliminating a notorious failure point in older engines where a single bad seal could blow the whole turbopump apart. Engineers avoided this design for decades because pumping hot, high-pressure oxygen basically turns your engine into a blowtorch trying to eat itself. SpaceX cracked it by inventing their own superalloy metal that resists the heat. Third, the manufacturing. For the Raptor 3, SpaceX leaned hard into 3D metal printing, literally printing the engine with the plumbing hidden inside its walls. By internalizing all those fiddly external pipes and wires, they deleted the need for a heavy heat shield entirely. The result is an engine that looks almost shockingly clean and simple, and it's 7% lighter than the Raptor 2 and 36% lighter than the original. The RS-25, by contrast, relies on thousands of hand-brazed tubes, a painstaking artisanal process that takes years per engine. But let's keep it real, because Flight 12 was not a clean sweep. Yes, the launch itself proved the Raptor 3's power beyond a doubt. All 33 engines lit, the stack pulled an aggressive roll maneuver, and the booster hit a record hot staging separation speed of around 5,700 kilometers an hour. The upper stage flew beautifully, even shrugging off the early shutdown of one of its vacuum engines, and it deployed its payload of mass simulators before splashing down precisely in the Indian Ocean. The engine's raw thrust? Absolutely vindicated. But the booster had a problem. About 1 minute and 40 seconds in, one engine shut down early. No big deal, the booster is built to handle that. The real trouble came on the way back. When the booster tried to flip around and relight its engines to fly home, several of them refused to ignite. SpaceX's own live commentator confirmed it on the broadcast. Fewer engines were lighting than expected. Without enough thrust to steer, the giant booster slammed into the Gulf of Mexico in a destructive splashdown. And on May 27th, the FAA grounded Starship pending an investigation. So the Raptor 3 is a beast on the way up, but reigniting it under brutal, real-world conditions is still a hurdle SpaceX is working through. This is bleeding-edge tech, still in its teething phase. And that brings us to the beautiful irony at the heart of all this. To land astronauts back on the moon, NASA's plan is to launch them on the SLS, riding those expensive throwaway RS-25 engines. But the actual lunar lander that touches down on the surface, that's Starship, powered by the Raptor. So NASA's own program depends on the very engine that's making its other engine look like a relic. And SpaceX hasn't exactly been quiet about it. Musk has openly mocked the old way of doing things, pointing out that the shuttle's so-called reusable parts were so hard to refurbish that they actually set back the whole idea of reusability for years. When he unveiled the Raptor 3, he called it simply a work of art. So, is the RS-25 truly obsolete? In pure physics, no. It remains one of the most efficient, most reliable engines humanity has ever created. And for the next few years of the Artemis program, NASA genuinely needs it. But in the world of economics and the future of spaceflight, absolutely. At $146 million a pop, thrown into the sea after one use, it simply cannot compete with an engine that costs a fraction as much, flies again and again, and rolls off the line every single day. The RS-25 is a gorgeous, expensive monument to the past. The Raptor 3 is the mass-produced workhorse that's going to carry us to Mars, and Flight 12 proved it's already here.